physics. But they were very simple. There was no reaction to shear forces. So if we imagine to take water, it has a very high Q. And if you want to cut it, you have no reaction. You can speak inside water, these bulk properties, compressions, rarefactions. Whales can speak inside water. But actually, if you apply shear force, there is pretty much no reaction. A viscous fluid actually is reacting to shear like in this way. So if you take a solid and you apply a shear force, well, you got something that is measured by one of elastic moduli. Because actually we consider lambda and mu. Rigidity modulus is taking care about the ratio between the shear force and the shear strain. But for fluids, ideal fluids, this is nothing. Okay? What about a viscous fluid? Well, if you imagine to apply a sort of a drag force here and to tear it, it's going to react, creating a velocity profile. And in the simplest case, the velocity profile that is created there is linear. That's a viscous fluid called Newtonian fluid. It's very simple. So the first part, I'm sure that you already covered Newtonian fluids in other courses. So we are going to use them. The key concept here is that we can have now a shear strain in a fluid, and you can imagine the delta x there. I'm going very fast here at the beginning because it's just a recap of many things there. So you can imagine to have a delta x on the top and to measure delta y along the profile. Then you can imagine to take the time derivative. That's the new part. And if you play with that, you see that you have a sort of a shear rate. The profile that is created in a very simple fluid is linear, like that. So if you take, you can imagine to take a stick, piece of wood there, and you pull it, apply a velocity. For an ideal fluid, a Pascalian fluid, an inviscid fluid, there is no reaction. You can pull it without any effort, okay? But in a viscous fluid, you are going to create a velocity profile here. With velocity that is going from the initial value, V0 on the top, to 0 because that's the bottom. The profile that is created there is linear. What does it mean? Well, that this slope is constant. Well, the measure of that constant is what is giving out viscosity. That usually is indicated with eta. Let me go here, where it is, and we have a strain rate. So rate means that there is time there. And this is what we need, trying to take care about the viscoelastic properties of some earth materials. So nothing is new here, except that we have a constitutive law for something that is not a rock, maybe, but maybe yes. And the plot here is stress. Which one? Shear stress. Here we have not strain, but strain rate. Time is there. And the profile is a line. The slope of that line is called viscosity. That's the simplest viscous fluid that we can imagine. And it is called Newtonian fluid. Now we use that, if you do remember. A long time ago, back in the past, let's see if I have, yes. One of the initial slides of a long time ago was this. We had a spring, a mass, Hooke's law is there, it's nice. But then we imagined that the oscillation was damped by a fluid here whose friction was dependent upon velocity. That's the trick for damped oscillators. Now, that was a Newtonian fluid because its velocity, it's constant. But B over M was gamma. And at that time, we used that definition to define what was called a quality factor. In the case of weak damping, that is what we discussed in wave physics course, we imagined that the oscillation sooner or later was going to cease, and the decay rate was decided by gamma. That is the unit of time inside. Okay, and then we defined what we call the quality factor at that time, with an initial definition that was the omega that was typical of the oscillator, and it was related by Hooke's law, like for example the square root of k over m. K is not with number, k is the spring constant, okay? Over this gamma here. Now, can we imagine some extremes here? Well, no gamma. A beautiful fluid that is not viscous. Immediately gamma is going to 0 and the quality factor is going to infinity, and no damping. On the other extreme, gamma is so high compared to, so large compared to omega 0 that you're not able to oscillate. Very high viscosity, very large viscosity. So you can imagine that this dual nature of eta or gamma is deciding the decay rate of something. At that time, we had just a very simple oscillator, and if we measure the decay rate of energy per time, well, that was Q. That was the first and very simple definition of Q that we did at that time. Se tu vuoi prendere queste lezioni sono nel corso di Wave Physics, che è parallelo. So, this is what we defined. So Q is definitely a measure of the quality of a system, and it is telling us how much energy is lost per cycle. It's a pure number, because actually, due to its definition here, omega is 1 over t, gamma is 1 over t. So it's a pure number. And actually, in this definition here, it's the delta E over E, pure number. You can imagine an infinite value for perfectly elastic systems, or very low values for something that is very damped. Okay? That was Q. No news there. Okay, so we're going to use the same trick. The viscous element there was deciding the quality. So what we're going to do now is to start again from viscosity definition with eta. We're going to use just this very simple definition, where eta is constant and it is deciding the line there. This is what we're going to use. We're going to mix this element with a spring, so like the damped oscillator at that time. But please do remember that for more complicated rheologies, maybe what you're going to use is something different, where you can put instead the constitutive law, and remembering that the viscosity of a material is decided by pressure and temperature, by, how to say, inner properties of that material. Please do also remember that some other constitutive laws are possible. If you're going to study polymers, a Newtonian fluid is not enough. Maybe you're going to study something that is plastic. You can imagine steel. You could say, oh, well, a bar of steel, it's very hard. It's very Hookean. You bang, okay? But if you increase the temperature, well, maybe steel can flow. So it could be, its rheology could be described by something that is called pseudoplastic. So it may be linear until a given value, when it's going to deform permanently, temperature and pressure. Or maybe what is called plastic, but nothing is occurring until you reach a threshold that usually is called yield stress. Okay? There are many rheologies. We're not going to consider them, but I added also this one. If in your future you're going to study, for example, deformation processes on long time scales that you're going to touch with Karim in its deformation, rock deformation course, maybe you will need to use something different than this. The most general law between stress, that usually is shear stress, and strain rate can be described by a power law. We're going to use just this one for today. Okay, so we are going to stay in the Newtonian fluids. What we are going to do next is the following. This is our target, trying to understand what we are going to call the creep curve. Pay attention, because when we consider, when we add to the system a time factor, then you could say, okay, how long is the observation time? For example, let's imagine that I'm staying here for 20 years. I'll get older than I am now, and maybe this table is going to deform very slowly and permanently. So I'm not going to knock it. Very short time, okay? Waves, mechanical waves. But maybe I can stay here and the table is going to deform. So you have always to remember the time factor is important, because maybe you can create mountains over very long times. So also something that is very solid with P waves, S waves, can behave like a fluid on very long time scales. So another keyword for today is creep. What is creep? Well, the study of deformation of something over a long time. So maybe on short time scales we can have immediate strain. So I knock, I'm straining, I'm applying a stress here. I'm going to cause something that is hooking, elastic. But then if I wait for some time and I apply a stress for long times, maybe I'm going to have a deformation time. So if you want rheology, it's the study of deformation of materials in time. Now what is solid, what is fluid can be very relative to time scale. That's the concept of rheology that you're going to explore also with career. Or if you're going to study material science, okay, that's rheology. For today, what we want to understand is we can describe an elasticity when a wave system is passing. So in relatively short time scales. But the same concepts can be used also to study deformation on long time scales. In any case, Hooke's law is not enough, because Hooke's law is just F, X, and the line, no time is there. You can run along that line, but nothing is lost there. So you can create work, but conservation of energy is valid forever in Hooke's law. So potential, kinetic forever. What we want to describe is a model that is allowing part of the energy lost in some time, along the time scales that are those pertinent of wave propagation inside the Earth. But with the same token, you can describe also the formation of very long time scales. This is what you're going to do. So actually the formalism that we are going to develop today, that is viscoelasticity, will be a mixture between what is in this red box here, that would be a viscous fluid. You can apply also for oceanography or I don't know what. An elastic solid, and this is what we have used to study waves, seismic waves, mechanical waves. And we're going to mix them in order to describe something that is viscoelastic. And viscoelastic means time is entering there, and you can use different time scales to study deformation on short time, deformation on long time. Okay? That's the frame where we're going to move. What we're going to do, and it's summarized if you want here. So take this definition of rheology, not for today, well, but forever, for your future career if you're going to study rheology. And it's a relatively young science, because it was starting in the 50s, in the 60s, when material science was going on, especially studying plastic materials, polymers, something like that. But the original definition was done by people that was working between chemistry and physics. And there is a nice time parameter here, and it's coming from something that is, okay, in the Holly textbook, it's called Deborah number, but actually is revealing on which side the material can be considered solid or liquid, or fluid if you want. And the idea was that everything could be considered a fluid or a liquid if you wait for enough time. Mountains can be flowing, they are flowing, but on very long time scales. So if you want, everything is decided by the time window of a process that you're considering, and the wave passage is very fast. Please do remember that, for example, when waves are traveling inside the Earth, if the source is enough powerful to make them to make the road along the circles there inside the Earth, they are taking, let's say, 3 hours to make the route. It's nothing. On that time scale, the mantle is behaving like a solid. But on long time scales, well, it's containing convection there. So you see that the concept of viscosity is allowing us to treat Earth materials for different purposes on different time scales. So you can imagine that viscosity of the mantle is very large, very, very large, but not infinite. So that if you wait enough, if you wait for enough time of the relaxation of the process, well, it's going to behave like a fluid maybe, whose Deborah number is going to 0. Okay? But it depends on the time window that you're considering. Well, for waves, the time of observation is so short that, okay, it's solid. But if you wait for the time scales of convection, well, in that case, it can behave like a fluid. So that's rheology. What we are going to do today is to consider this. Wow, nothing new here. It's a spring. And the spring is described by one simple parameter, a Hookean elastic modulus. In this context here, you can imagine shear stress and shear strain. I'm using G and not mu today because that's the letter that is used traditionally in viscoelasticity. It's an elastic modulus, okay? It's nice, no time is here. And so we can ask, okay, if we consider a spring-like system, what's going to happen in the time? Well, we can imagine 2 experiments. This is what we're going to do today, to apply 2 experiments to different systems. For this one, okay, we know the story. What if we apply stress? We take that system and we apply stress and we study deformation. Well, immediately we have a deformation. And until we leave the stress there, the deformation will be there. As soon as we remove the stress, and this is called the creep experiment, okay, immediately it will go back. There is no time, very simple. That's the creep experiment. What about the other possible experiment? Well, let's apply a deformation, let's study stress. Immediately it will be created. As soon as we remove the deformation, immediately the system will go back. Very simple and boring. So these are the 2 experiments. Let's imagine to apply strain with a step function. Immediately we're going to create a stress. How much? Well, it will be G, the elastic modulus, times the deformation. It will stay there. Okay? What about the creep? Okay, creep means let's apply stress and let's measure deformation. Immediately is going to be created. How much? Well, it depends by the stress and by the elastic modulus. Okay? There is no time here. It is pretty much enough to describe this kind of waves. But it's not allowing for the decay during propagation for an elasticity. Okay, can we use something else? Okay. Let's take this. That's the other extreme, a viscous element. Now this is a little bit more strange. What if we apply a stress there? Well, now we have to wait for some time. It will depend by the viscosity. Now we have another parameter, G. Please, let's remember units. What is the unit of G of the previous slides? Pardon? Are we sure? Remember, strain is a pure number. It's not that deformation has to be intended how much it has changed its dimensions over the initial dimension. It's a pure number. Deformation tensor, as we define, strain tensor is symmetric. It's containing just numbers, pure numbers. So please do remember that lambda and mu, they have the same units of stress. Okay? So it should be Newton over square meters, Pascal if you want. Okay? Now please do remember that here viscosity is containing time. Okay? Because now we have strain rate, so it's a pure number over time. So the units of eta are stress times a time. That's important. Now what if we perform the experiments there? Well, let's start with creep. Now we apply a stress and we measure the strain. Now strain will start, it will grow until we apply the stress there, then it's going to stop once we stop to apply the stress. And it has been deformed permanently. It's like if you take a piece of wood over water, viscous water, you pull it, you leave it, now it's not back into the equilibrium, now it has been moved. So you see that the deformation now it's growing. How much fast? Well, it depends. The slope will be 1 over eta. Now let's imagine some extremes here. What if eta is going to very large values, maybe infinite? We're not able to deform it. It's rigid in some way. So it will, if eta is very large here, the slope will be very low. We're not going to deform it. What if eta is going to 0? Well, it's going to be very easy. Now you take a piece of wood on the water, you pull it, almost immediately it's coming with you. For a pure ideal fluid, it's coming with you without any effort. Okay? Eta is measuring that. The resistance to shear, but in terms of strain rate. Now what is not exactly funny is that if now we imagine to apply a strain there with a step function, and since it's a Newtonian fluid, it will be reacting to time derivatives. So nothing here, we're going to have a spike just there. So stress and relaxation is not a relaxation at all, because stress will be alive just as a delta. So if you imagine to apply a strain there, you start reaction, and then if you leave a strain there, it's not going to react anymore because it's proportional to time derivative. Now you do understand this is not good for earth materials. But what if we mix elastic and viscous elements? How can we do that? Well, let's imagine to put them in series or in parallel. Those are the first two models. Let me tell you, and we're going to make some computation, but the role of the next slides is not to get you bored with algebra, just to have an idea about the reaction of these systems. Let me tell you that the first two ones, Maxwell and Kelvin Voigt, they are very nice. They can be used for other materials, but not for earth materials. They do not contain yet what we're looking for. But let's give a look. So we're going to create some networks, viscoelastic networks. You can do this with very complicated models. That's not my cup of tea. It's not important for seismology. Maybe for, if you are going to study polymers, you can do that. But we will start with something very simple, in series and in parallel, like very simple circuits. Now what about this? Well, if we put, let's imagine this will be the first one. Okay, let's go there. By the way, when you have a series system, you do understand that the stress applied to these two arms, it will be the same, but the deformation will be the sum. Okay, it's very intuitive. Now what about the parallel element? Well, now the deformation will be the same in the two arms, and the stress will be the sum. These are the rules. of a game that we are going to play. And let's play with the first. It's called Maxwell element. Okay, now we have two arms in series. Let's guess what's going to happen there. Well, let's imagine to pull it, to apply a strain. What about the stress? Well, part of the spring will react immediately, but the other element will need some time to develop its reaction. How much? Well, it depends on viscosity. You can imagine now that viscosity is infinite. Well, it's not going to move, and we have just a spring here. What if eta is very low? Well, it will follow pretty much immediately. But the point is that we will have time now entering inside the game. Now, if you do some algebra, it is not the focus of the lecture, just to create some plots there. And by the way, you have it, if you look with mathematical player, there you go. And you can change k here, that is the spring, the constant of the spring, and data that is, here it is mu, I'm sorry, but it should be viscosity. So you can play with these two to get these curves. Let's go back to our boring part. Now, for a series element, we have to sum the deformations. And which ones? Well, the time derivatives, because the other one is sensitive only to strain rate. So what we have to do is to do this algebra here, replace with the constitutive laws. Here we have stress, that's viscosity, that's G. Remember that the one has time inside. We say data, there is time. And the constitutive law, if you want, for this system here, is this one. Now let's give a look to this. Now if you give a look to eta over G, that's a time. Why? Because eta is a stress times a time, and if you divide it by stress, only one time is left. That is called a relaxation time. Now you could ask, why relaxation? Because now if you write, for example, the stress relaxation experiment, what does it mean? Okay, now let's apply the formation and let's measure the stress in time. What's going to happen there? Well, so this is the experiment that we're going to play. So you take something, you have to imagine to have this spring and the dashpot, and you apply the formation. And then you imagine to measure the stress there. One part will be taken immediately by the spring. Okay? How much? Well, it depends on G and by the deformation that you have applied. But now if you wait, the dashpot is going to act and it's going to relax the stress inside because it's taking its deformation. So actually you see that if you take the deformation there, for the pure Hookean element it would be always a stress there. But now it's going to be relaxed. How much fast? Well, it depends on that relaxation time. Could be very fast, could be never, viscosity is very large. But it's going to decay with time. The decay rate, so how long it will be important, it will be necessary to wait for stress to be relaxed, is decided by time. That's something new, because in the Hooke's law there is no time. Okay? What about the other experiment that we can imagine to play? Well, let's study Cree applying a stress. So now we have a stress time function that is like a boxcar. So we apply a stress at a given moment, we leave the stress there, we measure deformation, and then we stop applying stress. What is the plot? Well, immediately the spring will deform. How much? It will depend on G. But then also the dashpot is going to be deformed. How much? It depends on eta, because the slope will be dependent upon eta. Now when you do remove a stress, the elastic part will fade, will go to zero. So you have that. That's called recovery immediately. But a permanent deformation will be there, because the dashpot is a fluid. And so this has been left. That's permanent. How much? Well, it depends on viscosity. Okay, is that enough? No. It's nice, but it's not enough. Why? Because if you compare these two characteristic experiments, you see that's creep, that's a relaxation. For Maxwell, this is the summary. But if you take a realistic Earth material and you play those experiments, well, the response curves that you get are a little bit different. So that's not enough. Can we do better? Maybe. Let's try to consider the parallel case. Okay. It's called Kelvin void or Kelvin element, and it's like that. Now we do understand that the deformation will be the same in the two arms, and the stress will be the same. Let's write the constitutive laws, and this is what we get. Let's remember that eta contains a time. If we remember the definition of eta over g, that we called relaxation time in the Maxwell case, it will enter also in this case here. Let's give a look to an experiment here. Okay, for example, the creep. Now we apply a stress. And now we have the two arms in parallel, okay? Now let's imagine that eta is going to be infinite. We will never be able to pull, okay? So the spring could react immediately, but if eta is too large, we're not going to move that part. Now, what is the other extreme? Well, the case when eta is very low, maybe nothing, then the spring will take everything. So eta is going to decide how much time we do need to develop strain there. So this growth here depends on eta. Then, at a given point, until here, eta is going to deciding how fast the deformation will grow. Okay, and we stop. Now we leave it. The spring would react immediately, but the system is going to go back to the equilibrium, but with some time decided by eta. So it's a decay time, you see here. Again, related to that relaxation time. Okay, so we did something new here. Is that enough? No, because actually the Kelvin void model has something strange there. Why? Because if we now apply deformation and we study the stress, we got a delta, we got a spike in stress at the beginning. Because please do remember that this part here will react with the deformation. But here, you see, if you take this, and if you apply deformation there, the stress will be switched on just when deformation is going to change, because it's proportional to the time derivative. So you do understand that if you apply a deformation like a stepwise function like that, well, the dashpot will react, building a stress that will be there just for 1 second. Actually, in no time. Then if you leave a deformation there, it's going to be constant, so there is no strain rate. It's not going to build anything. And everything will be decided by the spring. That's not very realistic for an Earth material. So Kelvin void is giving us something different here, you see, because we have this building here that is more similar to this one. But in the relaxation, it's too sensitive to strain rate. Can we do something better? Yes, and the next one will be the last circuit that we're going to study. It's one realization of what is called standard linear solid, SNS. It's not standard, it's not linear, it's not exactly a solid, but that's the name. The realization that we are going to consider is called the Zener's realization, and it is this one. Now, is that at the Earth? No. But it contains enough parameters to let us to understand one very important thing. that now we will have two characteristic times. So we will have a dual nature of this system here. Okay, let's, before doing the, actually, just looking very quickly to the algebra of this constitutive law. What's going to happen there? Now let's imagine that eta is very large. If we apply experiments just one spring, we react this one. So if eta is large enough, that is infinite, we will have just one spring. So if eta is very tiny, is very weak, we will have two springs. So you do understand that if you want to characterize the equivalent elastic modulus of this system, well, it could be two. G2 or the sum of G1 and G2. It has a dual nature. Actually, if you write here the boring algebra, the constitutive law, what we have to do here is that now, at the end of this circuit, the deformation will be the same. And this deformation here will be the same, the two arms, but the stress here will be the sum of those one. So just a little bit more complicated. But if you write it, you see it here. Now, before exploring that expression, let's try just to think in very simple terms. Let's imagine that we are going to shake this strange system here with very fast perturbation. Okay, we're getting crazy and we're playing with that, with very high frequencies. You can imagine that with very high frequencies of perturbation, the time derivatives will be important. So actually, here we have a time derivative of stress, a time derivative of strain, averaged by what? By eta and G2. But eta is there. So at very fast, very high frequencies, G2 is an equivalent elastic modulus. Because only this and this will be important. On the other side, let's imagine to be very slow with our perturbation. Now you do understand that the time derivatives will not be important. What is going to be important is this term and this term. And now we have a stress, a strain, decided by another equivalent elastic modulus that is now containing the sum of G1 and G2. So the summary is the following, is that we have been used, starting with Hooke's law, with this. Stress and strain. In the middle, when we generalize to Hooke's law, stress tensor, strain tensor, 81 elements, but just 21, just 2 if we are living in an isotropic system, we have the elastic moduli that are deciding the ratio between stress and strain. Now, this is the generalization of this one, because now we have stress, strain, stress derivative, and strain derivative. Now it's containing 4 terms here. Which ones will be the most important? Well, it depends on our perturbation. So if we are shaking very fast this system, the derivatives will win. And the system will reveal itself with an equivalent elastic moduli that is G2. On the other side, if we are going to gently perturb it with very long times, time derivatives will not be effective there, and tau and gamma will be important. And so, G1 plus G2 will be there. So now you do understand that this system here, that is one example of what is called standard linear solid, contains a dual nature. It contains a relaxed modulus, a after a long time if you wait for a long time, or unrelaxed modulus if you are perturbing in a very fast way the system. So you can study rock deformation on long time scales, or deformation on very short time scales when a wave is passing. It's the simplest example of something that is containing stress and strain, Hooke's law, stress derivative and strain derivative. You have all the four terms. Okay. Now, if you perform some experiments here, for example, creep, what's going to happen here? Well, here we have our initial state. And now we apply a stress. What about deformation? Well, we will have a deformation that will be taken by the first spring, and it's decided by this amount here. And now if you take the stress for some time, the other one is going to build accordingly to eta. So now you have a reaction on very short time scales, and a reaction here on very long time scales. Now let's imagine to study what is going to call the creep function of this system here. What is creep? Well, it has to be something that is the ratio between the initial stress as input and the strain as output. That ratio will be a generalized modulus. And you see that now the generalized modulus has a reaction on short time scales and another reaction on long time scales. But it's the same system. Okay? Are you getting this point? So again, if you write the expression of what can be called the creep's function there, that is deformation as a function of time, it's described by this. Okay? What you're getting there, something that is not time dependent, is the first spring, this one. Let's imagine to pull it. That will take care of the initial part of the deformation. It will follow immediately. Okay, it's a spring. But then if you take the stress there, also the other one will act. Averaged in time, decided in time by eta. If eta is infinite, the other part will never follow. Ng2 will be the only one. Okay? If eta here is nothing, you will have two springs in series. And you have to sum, like in the circuits theory, the reciprocal of them. So that's it. It has a dual nature. One nature on short time scales, one nature on long time scales. Unrelaxed, relaxed. These are the keywords. But it has not anymore a single nature. One spring or two, well, it depends by it. Now, the following slides are terrible in this sense, in the algebraic sense. But on average, what we can say is that now, with that system, we can write what is called a creep function. What is a creep function? Well, it's the deformation in time. How can you define it? Well, it's the stress that you apply, and it's tau zero. It's like a black box, okay? You enter with tau zero and you measure deformation. How to describe deformation in time? It's called the creep's function. Now, if this is stress and this is deformation, how to define the parameters? Now the viscoelastic parameters. Well, let's take Hooke's law. That's the force, that's the deformation. So force over deformation is K. Okay? When we generalized it for elastic Hookean solids, we consider stress, strain. If we divide the input stress divided by the obtained strain, we get a modulus. Could be lambda or mu in that case. For the spring it was K. Now, for this system, that's the deformation, that's the input stress. Now, what is the equivalent modulus? Okay, it's this one. It's not 1, in the sense that it's decided by eta. It's not just G2, it's not just G1, could be the sum, everything is decided by eta in the middle. And eta, that is containing a stress times a time, contains a time. That's the relaxation time. So, again, you could say that system has an equivalent elastic modulus of G2. But then you can say, wait a second, because if we wait, also the other spring will act. And so this parameter here is deciding how much and when G1 is entering into the game. If you wait for enough time, this is going to 0, E2 minus, okay? And for very long times, actually, 1 over the equivalent elastic moduli will be the sum of 2 of them. So according to the time that you're deciding to observe your system, that's why it's a rheological system. On short time scales, you feel just G2. But on long time scales, you feel both. Okay? Unrelaxed, relaxed. Okay, that's for creep. Deformation. It's the generalization in time of deformation, if you want. For the generalized Hooke's law, we had no time. We didn't need any time there. And deformation and stress were decided, put together just by elastic moduli. Okay? Now we have something more. Because the reaction, it's viscoelastic, and it depends on time. And on how long time we're observing the system. Okay? Now that's creep. The other one experiment that we can imagine to perform is, okay, the first one we're studying deformation, and the second one we're studying stress. So we take that system, we apply deformation, and we study the stress inside. In the old Hookean world, that's easy. What about stress? Well, you take deformation, you get immediately that amount of stress. And the ratio between stress and strain is the equivalent, at that time was the elastic modulus. Okay, now what about the function of stress in time? Well, there it is. Now, if you see here, again, we have eta that is deciding the time. So, the time evolution of stress, let's imagine now we apply a deformation there, and now we are taking the whole system and we deform it. Okay? And now we're going to measure stress inside, in time. For the spring, okay, that's easy. Immediately as we apply deformation, we got that stress. But then now we have to remember that we have another spring in parallel with the dashboard. So in time, part of the stress will be relieved by the dashboard. And so, after some time, both of the springs will be entering inside the game. That's the time dependency. Now, if you want to describe the equivalent viscoelastic modulus, that's the function G. Now, that messy thing is saying to you, well, if you wait for enough time, that will go to 0. This will be 1, and now G will be a combination of both. Okay? If you don't wait for time, this will be entering with G1 minus G2 over G1. So you're going to feel another mixture. And again, if you don't have time to observe the system, you will get a feeling. But if you wait for a long time, so that this will go to 0, you will get another thing. That's a version of what is called standard linear solid. Now don't ask me why it's called standard, linear, and solid, because it's a mixture. So, the question, simple question here is, okay, this system here is G1, G2, or a combination? All of them. Everything is decided by eta. Could be just G2, the outer, could be both, if we wait for a long time. So it has a dual nature. Can this concept be generalized with the general standard linear solid? The answer is yes. And if you want, it's the summary for today. By the way, these are the curves that are typical of the standard linear solid. Now we are pretty much done. And it's enough for earth materials. But the summary for today, one of the summaries for today, is this. Now, what is this? It's the general constitutive law of what is called standard linear solid. Now, can we see something here that is a good old friend? Well, maybe yes. Let's imagine again that the time derivatives are not important. So we can wipe them out. This is out, this is out. What is left is a stress, a strain, and a modulus. So it's a good old K. Now, why there is an R there? Because it's called relaxed. So if you wait for a long time, so that the time derivatives are no more entering inside the game, you have an equivalent elastic system with a modulus that is called the relaxed modulus. Now wait a second. Let's imagine, as before, that we are shaking in a so fast way the system, but now the time derivatives are important. Okay, we can wipe this, we can wipe this. What is left is an MR times tau E and tau sigma. Now those times are called characteristic times, and as we have seen before in that special realization of a standard linear solid that is called the Zener's realization, they depend by G1, G2, and eta. Actually, those times are the two characteristic times of the two experiments that we performed. The creep experiment, does it mean creep? Let's apply a stress and let's measure deformation. We need some time. So, sorry, just to let you know. Tau epsilon in the previous realization was this. Tau sigma is this. They are not the same. They're not the same. They are both decided by eta, but one contains G1, the other one contains the sum of G1 and G2. One thing that is very nice that I'm telling now to you, let's imagine that eta is so large, so viscous, that is practically undeformable. What's going to happen here? That both times are going to infinite. Okay? So we can do whatever, but that part of a circuit will never enter inside the game. It will be just G2. So no need to invoke viscoelastic because one is fixed. We have just G2. The other extreme is when eta is very small, maybe going to 0. Now these two times are going to 0. What does it mean? That when we perturb the system, it will be G1 and G2 acting. Okay? Now tau sigma and tau epsilon, epsilon and sigma, in a general standard linear solid, they appear here. So, when time derivatives are very important, the system will behave like an elastic system. But now it's no more MR. It's MR times tau epsilon divided tau sigma. It's another modulus. It's called unrelaxed modulus. Now you could say, let's make a check again. Can we go back to the old beautiful Hookean nature? Oh yes. Then we can take out the derivatives and we're left with one elastic modulus. Okay? But if we have a viscoelastic circuit that is like a standard linear solid, we will have all the four terms. Stress and stress rate, use strain and strain rate. It's the viscoelastic part. And according to the experiments that we perform, we have two characteristic types. They have no meaning in the elastic world. Okay? But if the system is viscoelastic, now we have two time scales. One is for long times relaxed. The other one is for people that is in a hurry, unrelaxed. Now, is that the Earth? No. No, but it's a way to describe a part of the Earth. Which part? The part pertaining to dissipation. That's our topic for today. You can use the same model to study the formation of long time scales. Rock deformation, mountains building, okay? Karim. That's why Karim will use again this apparatus here, viscoelastic circuits, but to do something different. Now our target is go towards an elasticity of the Earth when a wave is passing there, okay? So if you want, on the unrelaxed part. Now what's next? Boring algebra now. Let me relax you on short time scales and on exact time scales. I will not ask you all the formulas that are here, okay? About this part, I will ask you the most important thing. The concept, if you want this, okay? You can remember that. Stress, strain, stress derivative, strain derivative. Easy, okay? But just to complete this vision of a standard linear solid, let's try to generalize the Cripps function and the stress relaxation function. You can prove that when you apply a stress with an Heaviside function, you can write a generic Cripps function. What is deformation in time? Okay, there you go. It's messy, but if you think about it, something is already in our pocket. It's this part here. For example, let's imagine that tau sigma and tau epsilon have no meaning or they are the same. Okay, this is vanishing. And we're just left with a stress over an elastic modulus. It's very relaxed one. Okay? So we have just add something. Still we have the elastic behavior there. Now, there is another way to write it, rearranging these terms. You can write it as the stress over the unrelaxed modulus if you wait for enough time. It's the dual nature. So, unrelaxed, relaxed. What does it mean? It depends on the time window that you are using to study your system. No time, you're in a hurry, okay, unrelaxed. Do you have enough time? Let's wait forever, relaxed. In these two extremes, the system is behaving like an elastic solid, but it's different on the two sides. And if you want, the relation between the relaxed and unrelaxed depends on the ratio between the two times. In the elastic, beautiful Hookean world, there was no way to introduce these ones. We get just one. But for SLS, now we have two, relaxed and unrelaxed. Now wait a second. If now the viscoelastic modulus is no more elastic, what about velocities? Well, the general feature of a velocity that we described in the wave physics course since the beginning, let's think about the velocity of waves in a string. Sorry for that. That was linear density, not rigidity modulus. It was attraction over something that was related to inertia density. Then sound waves. It was the bulk modulus over density. Still, something that is describing the property of a material to resist to the deformation over inertia. Bulk modulus, if you remember, was also called the uncompressibility modulus. If you take a diamond and if you apply pressure, you're not able to change volume as an extreme. And sound velocity was infinite. When you are considering your beautiful fluid dynamics and you are considering uncompressible fluids, you're letting sound wave velocity to squeeze at infinite. It's not infinite, but you want it infinite so you can take sound waves away to study other waves like gravity waves. So remember, uncompressibility is an hypothesis to clean things from something that is very fast. Okay, what about the other velocities? Well, P wave, now mu is a rigidity modulus, and S waves. Do you agree with me? Bulk, lambda, and shear, mu. What now? Because now lambda and mu have different nature here. We can find them somewhere. For example, on long time scales, MR, short time scales, MU, but they are different. Now, if lambda and mu are different for different frequencies, what is that? When velocity depends on frequency?
Has dispersion.
Right. So we have a dispersion now. Because high frequencies will fill the system with mu. Low frequencies, I'm not able to be so low, will fill the system like MR. So different frequencies will fill different velocities. And the summary, wait, that's terrible. The summary is this. Now, let's give a look to this. And let's take a brief. What do we have here? So all the messy slides that we did until now are plotted here. And it's not enough. Now what is that? Now we have two quantities. Let's give a look to this one first. Here we have frequency. High frequency, low frequency. Okay? Now these two extremes, unrelaxed, relaxed, they will have different values. Why? Because the equivalent elastic moduli will be different. Mu, Mr. So if you imagine to take the square root of both divided density, they will give us different values. That's dispersion. Second, we can prove that for standard linear solid, we have a Q value that is not constant, and 1 over Q that is absorption as a peak here. So we have an absorption peak. What does it mean? That frequency that are near to this one, that is the square root of the two characteristic times 1 over, they will be absorbed. So if you take that strange system, spring 1, spring 2, and the dashpot, and if you perturb it mechanically, on short-time scales, perturbation will travel with this. On long-time scales, it will travel with this, and these frequencies will be absorbed there inside. The algebraic part of this is this. I will not ask you at the exam the algebraic passages to arrive here. But please do remember one thing, that now, if you take the stress, that now is a function of time, over deformation, that is a function of time, and you can call that viscoelastic modulus, it can be written like a complex number. We have a real part and an imaginary part. Wait a second, if mu is equal to mr, so there is no difference between relaxed and unrelaxed, like in the classical Hookean system, this part will wipe out, this part will wipe out, and we're left with the good old world of Hookean solids. Okay? But if they are different, then this part is not zero, this part is not zero, we will have dispersion and absorption. If you want to generalize velocity as the square root of that messy thing over density, you get a function similar to this one, where still, if you put there mu equal to mr, we are getting the good old velocity. And q can be written like that. Actually, it's easier to write 1 over q, that is absorption, and it is like that. Wait a second, if mu is equal to mr, that's 0. So q is infinite. So these 40 messy slides let us just to consider a system that has a dual nature with dispersion, accordingly if mu is winning or mr is winning, with a q that is not infinite, but has 1 over q, a large peak at specific frequencies. But if you want to be lazy, let's put mu equal to mr, and all these 40 slides are nothing. Because then you get Hooke's law, normal C, and infinite q. Okay? That's the message, and that's the summary of the slides until now. So, we performed this long path through strange materials. But actually what we have been doing is relatively simple. We consider a spring, a dashpot, and try to put them together with the simplest circuit that is letting, that is called standard linear solid, whose constitutive law now has all the 4 terms, stress, strain, stress derivative, strain derivative, mixed together and are generalizing the concept of modulus. And now for the first time we have a complex modulus, and this means a complex velocity, that's only the absolute value, with a q that is not infinite. That's the summary. Is not the algebra. Is the summary clear to you? Okay? Now you should ask me, what about the Earth? Because with this, actually, we have simply considered this. Is that the Earth? For example, now you can play with K1, you can play with K2, you can play with eta, and what you're changing here is changing the constitutive law. Look, that stress, that strain, you see it's no more a line. At least it is made by 2 lines, but it's a curve. Is that enough for us? Yes and no. Because now the question should be, what is the Q of the Earth? Is it like this one? No. No. On one side, so that's the summary. Standard linear solid is giving to us, is providing to us dispersion and absorption peak. Now the question is, what is the Q of the Earth? And now this is what we're going to begin to answer today. I don't think we will be able to finish, but actually now we're approaching the end of the lecture, but we should try to understand. Let's imagine that now we have the Earth, okay? It's not nice, but we know that the Earth is not homogeneous. We have the crust, the mantle, blah, blah, blah. Every material of the Earth will have a Q in some way. But we are asking, what is on average the integral value of the Q of the Earth system? How can we measure that? Well, we have two ways. If we think about now to the basic definition of what is Q. We can imagine to take a wave train and to observe it while it's propagating. Now, every cycle, if Q is not infinite, of course, part of the energy will be lost. What is the decay rate of energy through a path? So that's the spatial measure of Q. Let's imagine to have surface waves running on the top of the Earth, and let's measure amplitude as it is decreasing in space. We have another possibility. Not to look in space, but in time. Now, let's imagine that we are considering the three modes of the Earth, and we stand. It's like a pendulum, right? Now, in time, what we have to measure is, for every cycle, how much energy is lost. That kind of measure, in principle, is made in the time domain. In practice, really looking at the three modes and how they are decreasing in time. Because every cycle, they will, like a large pendulum, part of the energy will be lost. So a spatial Q and a time Q. That's why what I was putting here was this slide here, that is a sort of a summary of what we can do in practice. But we're just spending one slide on that. Please do remember the definition of Q. In general, physically, it's the measure of delta E over E. Actually, 1 over Q is delta E over E, and 2 pi. If no loss of energy, Q is infinite. Strong delta E, Q is getting low. Okay, and you see that's the temporal decay in time of a standing wave. You can imagine also a string, okay? If you remember, actually, when we considered, I'm not going to play it again, but we used the loaded string applet. If you remember, I was plucking that string oscillating. There was a parameter that was called attenuation at that time. You can play with that again. And attenuation was deciding how long was the sound standing there. And visually, the amplitude was getting smaller and smaller. So it's like a free mode and waiting, measuring in time how long it's going to take to cease. It's like a pendulum there. Or again, you can measure, you can imagine the wave train that is traveling on the surface of the Earth, and you're measuring in distance how much energy, geometrically spreading apart, is lost. So that's why there are these two definitions. And they are talking each other in some way. And so this topic now, after that we have built the standard linear solid with its Debye, frequency peak, absorption peak, and blah, 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 is, okay, now let's imagine to play these two experiments in the Earth. So we can use the time domain, and now we are measuring amplitude in the different cycles. This is the number of cycles. You can write it in that way. Now Q is appearing. If Q is infinite, there is no decay. But after n cycles for large times, this is what we are looking for. Decay of amplitude in time. Please give a look to the definitions here, because omega is omega, Q is a pure number, and T is time. Or in space. And so now what we can measure is in one wavelength. What is the delta E? Remember that energy is proportional to the amplitude, to the square of the amplitude, okay? So we can build a sort of a differential equation for evolution of A in space. We can write it in that way with the Q definition, and we get this. Now, look, they are the same actually, but here time is space, divided velocity. So they are the same, but physically we're measuring two different Qs. Okay, both of them are the generalization of this, oh, one parenthesis is missing. If Q is infinite, that is enough. If it is not, we have decaying time and space. Now the question is, okay, what is the Q of the Earth if we measure it in that way? That's the answer. Second milestone for today, let's take a breath and look at that. It's not easy to answer, as we can imagine. For example, still there is a debate if you're looking at very high frequencies, body waves, or relatively low frequency, surface waves and modes. But let's say that for a large band of frequencies, the Q of the Earth is pretty much constant, and it is around, let's be inverse, 100 and 200. It's constant. But then, wait a second. We don't have a peak. So the Earth is not a standard linear solid. Should we throw away all the first 40 slides of the lecture? No. No, because actually, what we can imagine is that, and now we're going just to spend 1 second in material science, is that all the inner defects of a real Earth material at a microscopic scale. And if we imagine that anelasticity, intrinsic anelasticity, is due to defects that from a macroscopic point of view are letting amplitudes to decay, okay, that's the game, we can imagine that all these practical microscopic defects, and these are possible mechanisms at the microscopic scale of real anelasticity, if you put them together with different debye peaks, we can build what is called an absorption band. So the second summary for today is, for every real mechanism that is pretty much solid state physics of anelasticity, we can imagine that each mechanism can be associated to a standard linear solid, okay? And when you put them together, all those peaks are forming an absorption band. Now we are pretty much at the end. So we can use what we developed, the theory of the standard linear solid, that is going to be valid also for other topics. But for the Earth, we can take those strange spring dashpot systems, playing with G1, G2, and eta, and put them to pairs of solute atoms. That's one mechanism. Another one, grain boundary defects, microscopic, okay? So the Earth would be made by perfect crystals with no defects, maybe no dissipation. But in reality, we have many possible mechanisms. All of them, we build an SLS with different frequencies and absorption bands, and we can imagine to put them together, building an absorption band. So the second summary is, okay, we built a model, it's not the real Earth, but we can imagine to associate at a microscopic scale. And what we have on average is that now we are able to explain with a very simple, relatively simple model, the behavior of Q inside the Earth that for, let's say, for a large band of frequencies is pretty much constant, around 100. That's the second sum. So now you should say, okay, now we're done, we can finish the lecture. Now there is one additional feature. Because now we have a problem. And yes, we have time to discuss it. Now we have a problem. Why? Now let's imagine, now we have built our model of anelasticity. The main part of this model is that now, okay, we have created a set of complex viscoelastic moduli. Now velocities can be considered complex. wave number can be considered complex, and we have something that is decaying with distance, with the proper rate. And this is related to the fact that Q is not infinite. It's pretty much 100. It's quite a large value. It's not 1, it's 100. So it means that the Earth can sound for a long time. We have, on average, quite a good Q. Q100 is a large value. It means that oscillation. Okay, you imagine we're not removing a large part every cycle of. It's not a strongly damped system. It's quite a good quality. Now, with our model, what's going to happen? Well, now we have created a universe where lambda and mu are complex. What if we input a delta in our system, our Green's function? Okay, what's going to happen there? Well, okay, let's imagine that now we are plugging a delta in our system. What are the news now? Well, now we have a new filter. It's attenuation. And Q here is 100. Okay? Now, if you consider a delta traveling into this beautiful world with a constant quality factor that is 100, something is happening there. Because actually, if you let the delta there, and you consider this attenuation filter, what you're getting is this. You could say, ah, it's beautiful, it's very simple. A delta is a little bit spread now. Well, an elasticity is taking a delta and making it wider. And with a lower amplitude. Nice. But wait a second. What about this? Now let's imagine that we have a P wave. Nothing can be faster than a P wave. Okay? That's the maximum velocity valid to be causal in this universe. Information cannot arrive before. While this part of information is arriving before, it's not possible. For the principle of being causal, that part of a signal cannot arrive there. It should be later. There is only one way to take this signal here that is propagating inside our unelastic system and to put the arrivals at the proper time. There is only one possibility, and that's maybe the final news for today. The only way to let this beautiful curve with no acausal arrivals is dispersion. Now it's a strange logic. SLS has dispersion, MR and mu, okay? But we have just seen that inside the Earth, Q is constant, is not like that. We have to put a set of absorption bands, so there should be no dispersion, no more any dispersion for the SLS, because Q is constant. But now we need dispersion, because otherwise an arrival here, if you plug a delta here, someone can listen an arrival before it's going to arrive. That's not possible. The only way to put the things in the proper order is to let this C here disperse. And now wait a second, because C, this is P. There is no dispersion here. Given lambda, given mu, it's given. It's not frequency dependent. You could say, but SLS is giving dispersion. Yes, but we have a constant Q. So it's not that dispersion that we're looking for. With a constant Q, the only way here in this very simple system to let the things to arrive properly is to put dispersion, and that's before. It's called Asimi's law. Now you could say, what we're doing today, we are getting crazy. Wait a second, because these slides are coming from your textbook. So all this Okay, not all the viscoelastic slides that we discussed today are in the same session, but this part and the SLS are there. So you can easily reread that part in the same session. It's containing exactly this. So we're not doing exotic things. The final message to take home today is that after this strange and bizarre trip along springs, dashboards, viscoelastic circuits, Q of the Earth, constant, 100, being causal, we got at the end dispersion. This is not dispersion like the one that we study for surface waves. It's not due to the fact that dispersion was, we called it at that time, waveguide dispersion, because different frequencies were at different depths, if you remember, so filling different velocities. This dispersion here is there just for being causal in an unelastic world. It's an intrinsic dispersion. So now you can proudly say, also to your friends that are studying optics, but also the Earth as an intrinsic dispersion. Okay, the beautiful dispersion in optics is giving out rainbows. If you do remember, the dispersion for light in something that is not vacuum is due to the fact that you have refraction due to different velocities, different frequencies of the spectrum. You can have the rainbow. Okay? That's intrinsic dispersion. Because when EM waves are traveling inside a system that is not vacuum, they are dispersed intrinsically. Well, the Earth is doing the same to seismic waves, but just in a tiny way, because remember that this number here is a logarithm, so it's quite tiny, also because Q is relatively high. But we have a gentle dispersion also in body waves due to an elasticity and being causal. That's pretty much the end for today. It's not the end of these slides, because the remaining slides are, let's say, 5 or 6 slides. We're going to consider the first two, and they do contain really the summary here of what we do, what we have done into this lecture, but not the last two, because they can be used for the next. Okay, I cannot resist. That's the next and final topic of this course. So we're going to speak a little bit about seismic hazard in the next lecture and tsunami hazard and physics in the last lecture. So these slides can be taken for the start of the next lecture, but what we did in this today's messy lecture was a lot of things. The end of the story is that we created viscoelastic moduli to describe an elasticity of the Earth that on average can be described by a system with a constant Q for many frequencies of 100. Given that, to be causal, we need dispersion. Okay? Intrinsic dispersion related to an elasticity. And the summary is that what we considered as slowness in the wave physics course and until today, so 1 over velocity, now can be written in this way. If Q is infinite, this part is nothing, and we're going back to the good old elastic velocity. But today, we considered anelastic velocity. Anelastic velocity means that now we generalize the beautiful expression that we have used for harmonic waves. At that time, K was real. It was omega over velocity. Velocity was real, end of the story. But now, velocity is complex because moduli are complex. And so now we have something that is still related to the good old times, but C is no more the elastic C, is the anelastic, and we have now a factor that is describing the decay in space, and if you want in time, because x over c is the time, of amplitude. All the messy SLS stuff, given many SLS, creating an absorption band, is entering here. If Q is infinite, that is 0. Okay? But Q is not infinite. It's quite large, but it's not. Then, to take care about being causal, we have to consider a tiny factor of dispersion related to an elasticity. It's just tiny. It's a second order effect, but it's fair. If Q is infinite, everything is deleted. And the real end for today is this slide here. Because maybe in your future you're going to do some Q tomography, and maybe you're going to use it. But the summary is the following. That what we called wave velocity in the wave physics course and until this morning, slowness was just 1 over a real number. Now it's 1 over a real number plus something that is taking care about dissipation in space and time. Traditionally, this one, so 1 over, is called phase attenuation. This is what you have to remember, just terminology. Okay? It's the imaginary part. You can do for P waves, for S waves, for body waves, and for surface waves. So 1 over velocity, slowness, you remember the rate parameter that we considered a long time ago? Okay, that was slowness there. Now is replaced by a real part, that is a slowness, and this. Take attention here, pay attention to this one, because this has not the units of a velocity, it's the reciprocity, but it's called phase attenuation. So all the messy slides that we discussed today, it's just to make K complex, this K here complex, velocity complex, viscoelastic moduli, Q is 100, and now we have the possibility to study attenuation, and really to end two examples of, what is it? Some Q tomography. Because now you can measure Q, and for example, you can study, and you have to take care because Q is strongly dependent by materials, temperature, and pressure. That's why you can maybe decide to study Q of S wave velocities, P wave velocity, and to do some tomography. We will start from this concept, and with these 3 last slides in the next lecture, and really to end for today, the Q that I discussed with you, 100 on average, is an integral Q of the Earth. Of course, any material, you can imagine the Earth broken and flat, made by stack of materials. Every material has different Q. For example, shale, sandstone, granite, you see the numbers can be very different and can be very large. For example, in the mid-mantle, lower mantle, outer core, it's a liquid. It's beautiful, pretty much infinite Q. Because it's pretty much an ideal fluid. An ideal fluid has an infinite Q. Okay? So you see that for different Earth materials, these numbers can be very different. Can be very low, but not lower than some tens. Also for a sedimentary layer. Maybe the extreme is something like mud, but it has a Q of 10. It's not 1. It's not strongly damped. On average, if you take this vision as an integral, if you measure on the top with free modes or surface waves, it's 100 for many frequencies. Absorption band, SLS can be used to describe all of them, but constant Q is giving us also dispersion. That's the summary of all these pack of slides. Okay? So now you have a tool to describe an elasticity in the Earth. On a short-time scales, this reveals in attenuation of seismic waves. The same rheological concepts can be used on very long-time scales for rock deformation and mountain building. But that's for Karim's course. You will use the same concept of SLS, but relaxed, okay? Again, for the exam, just remember the milestones of today, not the algebra. Remember how we have played with Maxwell, Kelvin Voigt, Zener, SLS, Q100, and especially complex scale. And that causality means that we have a tiny dispersion. So the summary is also that in a beautiful, infinite, isotropic, unelastic medium, we have P waves, S waves, but a little bit dispersed. Because alpha and beta, now they contain a tiny part, frequency dependent, due to anelasticity if Q is constant. Okay, too many things for today. But from the next lecture, in the last two lectures, we are going to relax, not like a standard linear solid, a little bit discussing the application of these to some hazard concepts, okay? And Q will be important. Okay. If you want to play with those Mathematica, I'm not making any advertisement with Mathematica, but I know it's free for you, as far as I remember on the ICTP machines. The CDF player is free. I'm not using it just because it's nice to play with those tools. And if you Google and if you look, if you go to the demonstration page, and if you type Viscoelastic or what's the name of this one? Yeah, Viscoelastic, you can find those applets playing with the. Don't let me this ones, okay? Yeah. If you want to play, I found them on the web accidentally, so you can do the same. Okay.